Thanks to everybody for coming today. It's good to be here. So I'm going to try and persuade you that we need to stop emulating cameras in 3D graphics and start emulating human vision instead. And my name is Rob Pepperell. I'm from a company called Fovotec. We're based in Cardiff and London. The story really starts with vision itself. So all of us who are lucky enough to have healthy visual systems are able to open our eyes and experience this incredibly rich, deep, highly textured, highly detailed, colourful visual world around us. And if you start to lose that facility or lose it completely, it's obviously can be very problematic. So it's something we tend to take for granted, but it's an extraordinary capacity that we have. And actually no one quite knows how it works. The whole thing is a little bit of a mystery. But nevertheless, we have this extraordinary capacity. In what way can we capture that visual experience in media, and how can we present it in displays and so on? This is obviously a question that's fascinated people for a long, long time, artists in particular. I'm an artist by background, and this is really what got me into this question, trying to understand how I see and how I can record what I see. And so, we've developed all these incredible bits of technology for doing this, from just painting and drawing through to cameras, phones. We've got all kinds of display systems and so on that in various different ways capture the visual world and represent it to us as an image. And this technology is developing in extraordinary pace, as we all know from what we see around us at events like this. What underlies all that technology is a very, very simple mathematical principle that was actually discovered by artists and architects. And I like to point this out, being an artist myself. In about the 15th century in Italy, linear perspective, I'm sure probably most of you know this, it's a very simple geometric principle that allows you to project a three-dimensional space onto a two-dimensional plane. And if you stand in the right position, like this man is here, and look at the picture, you get more or less an exact replication of what's beyond the screen in the 3D space. Now that principle has served us extremely well for a very long time, and many, many technologies and processes exploit this simple principle and build upon it. Of course, it's really what drives photography. The whole history of photography is based on the same idea, projecting light through a lens onto a plate, capturing that light, fixing it, and creating images. And when computer graphics evolved in the late 70s, 80s, and so on, that same principle was adopted to drive the logic of the three-dimensional geometry inside the graphics engines, right from the very early days. And nowadays, with the sophisticated 3D engines we've got, like Unity here, inside the engine you have a virtual camera, and that virtual camera sits in front of the scene, captures all the light rays, projects them back to a virtual plane, and that's what you see ended up on the screen. Now, of course, computer graphics has come an extraordinary way in a very short time. Sorry, the screen's a little bit bleached out here, but this is just a clip I found on YouTube of someone rendering something in Unreal 5. And as you can see, computer graphics, real-time, highly textured, high resolution, high frame rates, incredible lighting effects, physics effects, and so on. So computer graphics is now an amazing tool that can produce pretty much photographic-like quality images. And nothing I'm going to say takes away from any of that today. But I do want to point out that there is a fundamental limitation in all this technology, which is that it is based on the camera model, on the linear perspective model. And this is something I realized quite late in life through a process of painting and drawing and comparing what I painted and drew to what I saw in photographs, that the camera model, the linear perspective model, isn't actually that good at capturing the visual world as we see it. It works in certain restricted ways very well, and it obviously has given rise to many, many incredible technologies that we use. But in lots of situations in everyday life, it turns out that it's not actually representing the world in the way that we know it to be. Particularly obvious, if you get pictures of people, we're very sensitive to proportions and distortions in people. So if you try to take a wide-angle photograph, for example, if you've got a wide-angle lens on an iPhone, say, you'll notice very quickly that you get these distortions. This is something that most people seem to have done. If you see an amazing full moon in the sky and it looks big and bright and highly detailed and so on, you whip out your phone to photograph it and you end up with something like this, which is nothing like what you experienced, obviously. And so imagine you're this woman here standing in this landscape, looking at the sunrise or the sunset, I can't remember which it is now, over this mountain range. What are you experiencing as a human being in that position, and how can you capture that experience? If we took she took a photograph of what she saw, it probably looked something like this. But in actual fact, she would have seen something that encompasses that entire pink area there. Human vision has an incredibly wide field of view, both horizontally and vertically. And a typical photograph, or even actually a 3D render on a computer, will tend to capture only a very small area of that total visual space in the middle. The reason for that is, in fact, there's many, many reasons, but one of the main reasons is that humans are not cameras. There's some similarity between the way the eye works and the way a camera works, but the similarity is not very deep and it ends very quickly. Most of what we see is not driven by what goes into our eyes, it's by what happens in our visual brain at the back of our head here. That's what constructs this rich, dynamic, volumetric space that we experience. And so we see with our brains as much as we see with our eyes. In fact, in some ways more. You can dream, you can see in dreams without having any visual input at all. So, just to give a very, this is a short list, but just give you some idea of the difference. In human vision, you have very wide fields of view. Cameras tend to have much more narrow ones. Human vision is dynamic. It's always changing. Wherever you look, your eyeballs are moving and so on. Cameras tend to be quite fixed. Your experience of space is very deep. Cameras are obviously produce flat images. We tend to have two eyes. Most people see with two eyes, and they interact with each other to give you binocular vision. Generally, cameras are monocular. And human vision is embodied. You're moving around the world inside your body. A camera is just like a fixed box. So there's others, but that gives you some flavour of the differences between the two ways of seeing the world. So I'm going to argue that we need to move away from this kind of virtual camera model, which is embedded very deeply into all our imaging technology, and particularly in our graphics engines, and move towards a much more human-centered model of imaging. And I'm just going to tell you very, very briefly how I came to do this. And as I said, I'm an artist. I came to this by trying to paint and draw what I could see and realizing that I couldn't do it in the conventional way that I've been trained to draw. So if I was trying to draw these flowers in the middle here, I would typically draw something that looks like that. But when I tried to draw my full visual experience, in other words, everything I could see all around me, this is what I ended up painting. This painting is a kind of map of my perceptual structure, if you like, when I'm looking at those flowers in the middle there. And I can photograph this scene with a conventional camera, but it looks very, very different, as you can see, from what I painted. So this is the raw difference, if you like, between a linear perspective render of a scene and my recording of my perceptual experience. And there's all kinds of things going on in the painting that don't happen in the picture. My own nose appears in it, for example. There's doubling going on. There's many, many things I could talk about, but you can see immediately that there's a great deal of difference between them. And I'm not going to go into this in detail, but in our lab in Cardiff, we tried to study this scientifically, or we did study it scientifically, because when we looked into the literature, no one else had really looked at this problem in vision science. Vision scientists tend to be interested in the middle area of vision, not this much wider space around the periphery. So we set out building apparatus like this to try and measure that. And we built this device that we put people in and asked them to report what they saw. We compared standard projections like this to ones that I made from drawing of my own visual experience. And we found, for example, in this study that people rated the artistic one, the one I drew, as being much closer to what they saw than the geometrically generated ones. This is another piece of apparatus we built, which was a volumetric space that had a red ball in it. And I did lots and lots of drawings of this space with these data points on. And this was the point at which we were trying to kind of mathematically model this rather than just draw it in subjectively. And then we started building real 3D spaces, taking drawings of them, and trying to get computer graphics engines to conform to the perceptual structure. As you know, I'm sure you all know, 3D graphics engines are linear perspective devices. That's the fundamental geometry they use. To get them to do something else is incredibly difficult. You're working against everything from the hardware up. Years and years of optimization to make linear perspective run efficiently. You have to kind of get around that or get rid of it to some extent to do these non-linear transformations that we were doing here. But the end result, and this is actually quite an old piece of tech now, but the end result was a version we built in Unity of a kind of real-time model that's based on an avatar's eyes walking around a space. This was on a very big screen, and if you stood in the right place and looked into the middle, you got this very strong sense of depth and immersion, because it was showing you everything you would see if you were actually in that space. Normally you don't see that in a 3D render. And we also experimented with lots of things like eye tracking. So in this example, this is Ali, my colleague, who built all this. You can see that the eye tracking is driving the geometry. So the model is changing in real time depending on where he's looking. So there's all kinds of things that you can do with building the dynamics of human behavior into the image as well, which are interesting. I'm not really going to talk about those today. I'm just going to show you what we currently have in terms of a tool, which is a version of, mainly actually in Unreal, but we have other versions running too, which is a kind of reconfigured engine, a rendering engine, if you like. I don't know why this is jerking. It's very annoying. I've been trying to fix it all afternoon. But anyway, something to do with Keynote on the Mac. That you can see this is a linear perspective render here, and it's transforming or morphing into what we call a Fovo render, which is based on this structure of human visual space. And as you can see, in the linear perspective version, things look very stretchy. The middle looks very far away and minified. In the natural version, as we call it, everything looks more or less as you'd expect it to look if you were actually in that room. And this is our benchmark. What does things look like when a human is actually there? So lots of people are using this now in architectural visualization. For example, this is a linear perspective render, just to show you a couple of differences. And this is our render of the same field of view, but it has a very different, so if you look at this chair, for example, this looks much more kind of natural in terms of its shape. In real-time gaming applications, this is an ultra-wide field of view here. If you want to get a lot of people in at once, in fact, it was a metaverse company who alerted us to this problem. They wanted to show big crowd or lots of people interacting in a crowd, and they couldn't get everyone in without them looking all squashed. But using this technique, you can greatly improve that visual experience. And then we've got a lot of people working in automotive. This is a wide-angle view of an interior of a car, and then this is one that we've modified. And we benchmark this against reality. We use our own visual experience to say, well, what does this look like, and how close can we get to that using the computer graphic tools? There's two aspects of the technology that I want to point out. One is this extra breadth or width you can get. The other is the flexible nature of the process. And actually, this was a kind of byproduct almost of us trying to get this more expanded field of view, because we found we had to break apart the 3D engine to get this to work. And in doing so, we gave ourselves access to all kinds of parameters that aren't normally available to a 3D artist. You can change things in depth rather than just on the flat plane. And another interesting area, and this is something we're developing at the moment, is starting to build intelligence into the image. So rather than the camera being a kind of a mute or a dumb box that just moves around in virtual space, it's starting to know what it's looking at and adjust its geometry in real time accordingly. So in this top render here, which is the one that's got this adaptive technology built in, it's adjusting itself in real time to give you the optimal view. If you compare it to the linear one in the top here, or the other standard renders, you can see that it has this much more natural feel to it. So we're starting to move into intelligence, thinking about AI, and how integrating AI can, again, improve the structure and quality of the image experience. So that's my conclusion, really. 3D graphics can be improved even further if we stop emulating the camera and start emulating human vision. And I just want to thank some of my colleagues who've worked with me on this project. Thank you.
One of the things that I noticed is that on that den, the motion sickness, the feeling of motion sickness is a lot less. Have you done any looking into that?
We have, yeah. I mean, one of the things you get with wide-angle linear perspective shots is you get a lot of space moving very fast because it gets stretched. And if you do A/B comparisons, you'll notice that the speed difference is very, very different because this far less space has to go past in the same time. So you're right, yeah. It's more natural in speed, but also in distance judgment. So we've got a paper coming out soon which shows people are much more accurate in estimating how far things are away from them in 3D space. So those kind of, those subtle perceptual cues do make a difference to your experience of the scene.
Cool. Still another minute or so. Any other questions?
Have you done any studies separating out how women and how men see?
No. I don't think we've ever...
My wife sees things that are very different to me all the time, so...
Virtual reality, it's been proven that women experience it very differently, so that's not a facetious comment.
No.
I wasn't being, by the way, I wasn't.
You're being heckled from behind, so it's a serious question.
What we have found is a lot of variation amongst people in how they do perceive.
Yes.
So we tend to think everyone sees the world the same way, but our experiments found not. You get extreme differences. Most people are kind of roughly the same in the middle, but you do get these kind of outliers. You see the world very differently from other people.
Literally.
Yeah, exactly. Yeah.
Good question. Have you, or do you have any plans to kind of like introduce any sort of spatial audio like ambient sonics? Because it does VR development has a big impact on that kind of perception.
Yeah, no, I think what we're doing here visually you could also do with sound. We have played a bit with sound, and it does make a big difference as you'd expect, but we've never put the kind of R&D into that side of it in the same way. We've talked to sound psychologists and so on, and they've said there are very similar things going on in auditory perception. But no, we would love to do that. We do, I haven't shown it here, but we do a lot with displays as well. So we do a lot of stuff with non-flat. Most of those paintings I showed you are not actually painted on flat surfaces.
Right.
They're all on kind of curvy surfaces, and we also project a lot onto curvy surfaces, and that makes a huge difference too. You can get very strong sense of depth and emotion by kind of deforming the surface. So all these cues can all work together to give you a stronger perceptual experience.
Thank you.
Does the same distortion apply if you're just covering one eye?
It does, and actually, funnily enough, the depth effect gets much stronger with one eye than two, because we're using monocular depth cues, they're called, rather than binocular. So actually, we've had some very strange experiences with people who've never seen depth before, because they've only got one eye, or they can't fuse their eyes, and they suddenly see depth for the first time, because it's working on a monocular basis rather than binocular. It's a very different approach to VR, which is obviously based on binocular fusion and so on. It's amazing how much, I haven't shown you here, but it's amazing how much depth you can get people to see, or just on a flat image, if you set it up in the right way, because it kind of tricks their visual system to thinking they're seeing depth where there isn't any. So actually it's a good question. One eye can actually be stronger than two. Yeah.
So are you selling this software now?
We're more interested in people using it at the moment. Right. Yeah, I mean we have a licensing. We do license it to people, but we have a much longer term goal to get this kind of available for everybody. Really, that's what we're trying to do long term. But anyone who wants to use it, we can give them a evaluation license, and they can. It's in Unreal 4.2.7 at the moment. Is the best version. We're working on Unreal 5, and there's other renderers as well we support. So anyone who's interested in trying it, get in touch, and we can set you up as an evaluation license. Yeah. Yeah. Great. Okay.
Thank you
very much.
Thank you.
Thank you.
Thanks.